This is Precalculus, section 1.5, Parametric Relations and Inverses. So by the end of this lesson, you'll be able to define functions and relations parametrically, and we'll be able to find inverses of functions and relations. So basically, if we're talking parametric relations, what we're doing is we are using two equations with a third variable to describe what we used to describe in one equation and two variables. Another natural way to define functions, or more generally relations, is to define both elements of the ordered pair xy in terms of another variable t, and we call that variable t the parameter. So here's an example of defining a function parametrically. Considered all the ordered pairs xy, so all the points xy that are defined by x equals t minus 1 and y equals t squared plus 2. The question then is find the points determined by t equals negative 3, negative 2, negative 1, 0, 1, 2, 3. So basically the way this works is you will have two equations and those two equations will determine all the points that you would graph for your function. So how it works is you plug in all the different possible points for t. Whatever you plug in for this x, or for the t in this equation with an x, you plug in for this equation with for t with that has a y, and the answer you get for what x equals and the answer you get for what y equals becomes the xy coordinate point. So for example, if I plug in a negative 3 for here for t minus 1, I'd take negative 3 minus 1 and get negative 4. If I do the same thing and plug a negative 3 in for here in this y equation, y equals equation, I'd take negative 3 squared plus 2, which would be 11. That tells me that when I use the parameter of negative 3, I get negative 4, 11 as my coordinate point. So you can pause right now and do this, or understand that if you plugged in negative 2, negative 1, 0, 1, 2, 3, you get these x values, these y values, and all these coordinate points. You graph all these coordinate points, and you get some function or some graph that maybe you wouldn't expect. What's really nice, and you probably never knew about, is that you can graph parametric equations on your graphing calculator. Normally when you go on your graphing calculator, it looks like this. But if you go to mode, you don't need second, I guess. If you click on mode, normally the normal setting is to be on function. If you click to the right, that par, you probably always thought that was like you're gonna go golfing or mini putting or something. No, that stands for parametric function or parametric equation. Click on that, and then notice when you go to y equals, you've got an x equation and a y equals equation, just like we did in this problem where you plugged in points. Now, before you just go ahead and graph that, I already plugged them in here. You can do the same. You can pause this whenever you need to. Before you graph that, you want to go to your window. What you want to do is take a look at what's different. There's a T-min, T-max, and a T-step. Basically, what this is showing is what values do you want to plug in for T to show to graph. Now, here's where you got to be careful. If you have or what you put in here determines what your graph is going to look like. So T-min, T-max, that's what the grapher is going to plot. It's going to plot the points from negative 3 to 3. The T-step is how often it'll plot points. What I mean by that is, right now the t-step is 1. Well, that means it's going to plot a point every 1 t-value, just like we did. So basically, if you were to graph what we did in this chart, and then connect the lines and continue those lines out accordingly, that's the graph that this grapher will show. If you change this t-step to a smaller increment, what's going to happen is it's going to graph more points and become more accurate. It's kind of a game of give and take. The smaller the t-steps and the wider the t-min and max range, the longer it will take your calculator to graph this function, because it'll have to plot more points. Understand that the grapher then is just going to connect all those points and make a graph look as accurate as possible. And then the x-min, x-max, x-scale, and then y-min, y-max, y-scale are all the same as they've always been. So I'm gonna leave the t-min max as it is and just take a look at that graph. And then what I'll do is I'll adjust the window a little bit. We don't need the y values to be so low. So I'm just going to change my y minimum to 0, my y maximum to 20 to adjust my window. Graph that again, and you can see that it just stops right there and right there. Well, that's because of the restriction on our t values. If I go back and I change my t minimum, let's say to -10 now, take a look at how the graph is adjusted. Kept going. If I change my window again and change that t-step to 5, now it's only going to plot every 5 points, or every 5 t values. It's going to look a lot different because there's just not enough data points to make an accurate graph. If I adjust this one, we'll go farther to the right. If I change this to a smaller increment, the graph should get more accurate, and so on. So, like I said, it's a game of give and take. Now you have this this option. Just remember, if you put it in parametric mode, you go here to change back to function. So now in this example, we're going to define a function parametrically. Consider all the ordered pairs x, y defined by this parametric function. X equals t minus 1, y equals t squared plus 2, the same one we've been working with. Now, we're going to find an algebraic relationship between x and y. Is y a function of x then, is the question. And so what we'll do is we will use substitution, generally, to combine the x and y into one statement and get rid of the t values. So the logical step would be to take this first parameter and solve for t. So t would equal x plus 1 if I simply add 1 to both sides. Now I can take and replace the t in the second equation with an x plus 1. And when I do that, and then multiply out and combine like terms, I can see what I'm actually dealing with. This parametric function is the same as this quadratic, or this parabola. Is it a function? Well, yes, we know it's a function because it's the graph of a parabola. I could use the vertical line test, bring my vertical line across, and for every x value I have only one y value back out. We also have, let me scroll this down, what's called an inverse relation. The ordered pair AB is in a relation if and only if the pair BA is in the inverse relation. Basically what that's saying is if you take a function and you take its inverse function, every every point that's on the function will have an inverse corresponding point that simply reverses the two numbers, the x and the y, around. One way to look at that, I'll talk about in a second, is to use the line y equals x. So we now have what's called a horizontal line test. Remember, we had the vertical line test, and that was used to determine if something was a function. A horizontal line test, the inverse of a relation is a function if and only if each horizontal line intersects the graph of the original relation in at most one point. What that means is I can take the graph of my function. Oops. I can take the graph of my function, and if the original graph that I have, if I use a horizontal line test, and that line does not cross the graph in more than one spot, then that would tell me that the inverse of that function is a function. Now, when we're talking about an inverse function, here's kind of the rule. If the function f, or f of x, is a one-to-one function, so that's a new term. I believe that's a new term to you. If it's one-to-one, and it has domain D and range R, then its inverse function of f, we denote with a exponent of -1. So f, this means the inverse of the function f is going to be a function with domain R and range D, defined by f inverse of x, or f inverse of b, is going to equal a if and only if f of a equals b. So basically what all that says is, or the big point here is, if you have some function f, it is one-to-one with function f inverse if the function f has domain D and range R, and the inverse has domain R and range D. And basically, every point AB from the function f corresponds to a point BA. That should become more clear on the next. So what I was just describing was algebraically how you can see how, or numerically, if you will, how you can see how one function would be the inverse of another. Graphically, we use the inverse reflection principle. The points AB and BA in a coordinate plane are symmetric with respect to the line y equals x. The points AB and BA are reflections of each other across the line y equals x. So graphically, if I wanted to find the inverse of this function, or I wanted to graph it, what I would do is I would consider the line y equals x. So that's the line that goes through the origin, through point 1, 1, 2, 2, and so on. I would graph that line, and I would literally reflect the function across or in the line y equals x. That function would then be the inverse function of this blue one. I'll show a nice graphic here to relate that. And then it says, is f a one-to-one function? Well, first we check the vertical line test. Is it a function? Yes. Remember, that's where I take my vertical line, drag it across the graph, and if that vertical line never crosses the graph in more than one spot, it is a function. I then take that line, make it horizontal, and bring it vertically. This will tell me if the inverse of that function is a function. So if it never crosses the graph in more than one spot, then the inverse will also be a function. That tells me a graph is one-to-one So if it passes the horizontal and vertical line tests, the graph is 1-to-1. So the nice graphic I have for you is this. I just drew that red line earlier. That's the mirror line. I then reflect it across. All of these points reflect across to here. All of these blue points reflect across to these black ones. The result is the inverse function. So this graph is the inverse of the blue one. Pretty cool, I know. How would we find the inverse function algebraically? It's really quite easy. All you need to do is switch the x and the y around and solve for y. So take the function you start with, define its inverse function, you rewrite it as y equals 2x over x minus 1, or consider it that way, and then switch the x's and y's around, as I've done here. Now solve for y. How do you solve for y? Well, multiply both sides by y minus 1, distribute, isolate the y terms. Okay, so here I brought the negative x over, brought the 2y to the other side. We've isolated the y terms on one side. Now factor out a y. This has a y, this has a y. Factor that y out. Divide by x minus 2. Let's bring this back up a little. And now you've got the inverse function. It's that simple. Remember, you can always pause and rewind if you need to. I gotta get moving. These videos I'm trying to make less than 20 minutes. Also algebraically now. Algebraically, how do you determine if it's 1-to-1? Remember, use the vertical and horizontal line test to see if it's 1-to-1 graphically. Algebraically, you use compositions. This is what we did in section 1.4. If you take f of g of x, simplify it all the way down, and it simplifies down to x for every x in the domain of g. And you take g of f of x, and that simplifies all the way down to x for every x in the domain f. Then the function is 1-to-1. I'll just show you a quick example here. If f of x is x cubed plus 2, and g of x is the cube root of x minus 2, we're going to show that those are inverse functions. We use the inverse composition rule. First check f of g of x. Remember what that means is I'm going to take my f of x function, and anywhere an x occurs, that's just right here, I'm replacing that x with the entire g of x function. That's going to go right in there, as you can see here. Simplify that out. The cube root is canceled out by the cube. X minus 2 plus 2 is x. Good, we're halfway home. That one equaled out to x. Now, if g of f of x also does, then we've found what we're looking for. We've shown that they are inverse functions. So again, I'm going to take my g of x function this time and replace this x with the entire f of x function. That's what's happened here. X cubed plus 2 minus 2, all under the cube root. Well, you don't really need those parentheses anymore. The 2's will cancel out. You're taking the cube root of x cubed. That equals x. So you've just found, since both f of g of x and g of f of x equal x, f and g are inverses. And that works for all x values. So how do you find an inverse function algebraically? You determine that there is an inverse function by checking if it's 1-to-1. State any restrictions on the domain of f, the original function. So what that means is if there's any restrictions on the original function, then those restrictions will carry through to the inverse function as well. So for instance, if we're saying that g of x, in this case, if we were saying that was the original function, if there were any restrictions on that domain, then they would carry through to the end. After you've determined that, switch x and y in the formula y equals f of x. Solve for y to get the formula y equals f inverse of x, and then state any restrictions on the domain of that inverse. That's it. So this is the lesson. It's about 20 minutes. You should be able to get through the first assignment for 1.5, and I look forward to your questions in class.